sitting here looking at myself wondering, does my lack of hair make my head look bald? Oh boy.
Your stream setup looks a little different. Did you change anything?
Yeah, I'm actually sitting down this time instead of standing. It's still the same thing, except normally I'm up here and I'm standing, but
Yeah, I think I do recognize that actually.
I've got my cool shirt on. Holy shift. Can y'all read that?
Yeah.
Yeah.
My mom, my wife, and my brother were all getting on me the other day, like, you need to dress nicer. You look so handsome wearing nice clothes. I said, I feel so awfully uncomfortable wearing nice clothes. I really like wearing my t-shirt. Leave me alone.
I have a shirt that says, you matter unless you multiply yourself by the speed of light square, then you energy.
Then you energy. I like it.
Excuse me, sir.
Yes, ma'am.
In your email last night about the constants at the front of the book, for those of us who have the digital book, we don't have constant pages in the front matter.
It should
but
have
we
to
do
be like an appendix or something.
We do have them in the end papers, and I just wanted to double check that those were the correct ones.
Absolutely, yeah. And any stuff that's sort of printed in tabular form, or just like someone sneezed it onto a page on the textbook that's got constants and prefixes, you're welcome to any of that stuff.
Okay, thank you.
No problem. Good question, Cadmium. So, anybody else have any questions? Man, my baldness is really bothering me today. Oh well, let's go for it. Actually, the reason why my brother and my mom and my wife were talking about it is my brother didn't realize about a year ago I took a picture of the rock and I used Snapchat to cut my head off and put it on the rock's body. My head's in there in this awesome shirt, and the rock sitting here like this with his big ass hand, with his big hands. And actually, as soon as I posted, like, everybody's like, "Wow, you look really good, Billy." I was like, "Yeah, it's me. Yeah, sure." All right, I guess we should go ahead and get started on the physics-related topics. Never mind all this fun stuff. So we have introduced, last time I introduced the idea of the work energy theorem. I've showed you a couple line integrals using, work equals the integral of f dot dl as a line integral. And I showed you how you have to choose the dl or the range of integration to indicate the direction you're integrating. But you can't choose both. In other words, one of them has to point in the correct direction, and the other one just has to go in the positive coordinate direction. So in direction of increasing coordinates. So if you're integrating with respect to x, then it has to go in the positive x direction. Or if you're also, if you're integrating with respect to x and you want to use the dx to indicate, as opposed to the, or if you want to use the range of integration to indicate the direction, then of course you use dx in the positive direction, so it'd be positive dx I hat. If you want to use the other part, then you just need to make it go from small x to large x in the range of integration when you're doing it with dx. I mean, when you're doing it with the dl. So just keep that in mind. I know me saying it is a lot harder for you to understand than the examples I work for you. So I'm going to do one example today that shows you another force acting as a function of position. So we'll do another line integral, in other words. And what I'm going to do is I'm going to basically use it to calculate the work done in removing an object on the surface of the Earth from the gravitational potential of the Earth. In other words, moving it so far that gravity cannot touch it anymore. And that actually turns out to be called the potential energy function, because actually sort of the negative of it, the potential energy is always the negative, the change in potential energy is always the negative of the work done. So it's a good, nice example. And then after that, I can use it to derive something kind of interesting. And the thing I'm going to derive is basically the Schwarzschild radius, which turns out, even though I'm doing it with Newton's laws of physics, turns out to give you the exact right formula. Chapter homework is not due on 10/11, chapter 8, that is chapter 7. We have due Sunday for the concept questions, and I think Wednesday is for the actual questions or calculational problems. And then the following week will be chapter 8, even though our test is supposed to be, I think, on Wednesday, which does cover chapter 8, by the way, our midterm. So all of those midterms should be up and ready to roll now. Y'all need to take the respondus one immediately. And not only that, that one you don't count towards your grade, but it helps you make sure you're ready to run the lockdown browser and the video cam and all that stuff. Remember, you have to have a video cam, or you have to set up a proctor to proctor the test for you. So let's go ahead and get started on this part. And I don't always put the assignments in the Canvas module link because it really is time consuming. It literally takes me like 8 minutes to do one of them. But I've been trying to do that all semester, because once I do it once, then I can always paste the course over to the next course the following year. So I'm going to try to do that, but I don't necessarily get that. So just remember, you need to be responsible for your due dates. And we essentially have a homework assignment due every Sunday and every Wednesday. It's usually the concept questions on Sunday and the work problems on Wednesday. All right, so remember, our formula for work is equal to the integral of f dot dl. Let's imagine planet Earth is here, and it has a radius given by r with a circle and a plus sign. That's the symbol that we use for the planet Earth. And let's imagine an object of mass m on the surface of the Earth, and we're going to apply a force that direction. And that's, you can see in this case, if I called this the y-axis and this the x-axis, I'd be going in the x direction. But in general, in any coordinate system, I could put the origin at the center of the Earth and then just use this as radial direction, and it will cover everything. And it always does, just by the symmetry. But I'm going to use the r hat vector again for that, even though, like I said, you can completely use the x. And this is going to basically go to r equals infinity. So when I do that, that's going to give us actually the work done in escaping the gravitational well of the Earth. Okay. Now in the part B, I'm going to actually use that and say, let's pretend all that energy that the work needs to supply is just coming from something called the kinetic energy, which y'all have been introduced to, of this object. And in fact, let's pretend that it can only do it if the thing is going at the speed of light, because if that's the case, then you're right at the edge of where something becomes a black hole. A black hole is something where not even light can escape. So if we say only at the speed of light could you possibly escape, then you're right at the edge of how small you need the Earth to be a black hole. And in fact, if you go any smaller, it will definitely be a black hole. So it turns out the formula that you get is right. So we're going to do that. So first I want to know what work is required. And I'm going to work it all in terms of symbols, so we'll have a nice, neat formula to finish up with. And then, of course, you can even, I'm doing it for the Earth, so it'll have the mass of the Earth and all that stuff in it, and the mass of the satellite. But you could just change it to the mass of whatever body you want and the radius of whatever body you want. So we'll see. And then part B, how small should Earth be to be a black hole? And I'll give you a bonus formula for that too. In other words, I'm going to give you the escape velocity of a planet, and that again will be for the Earth, but the general form, just replacing the m and the r, will give you the escape velocity for anybody, the sun, a human, whatever you want. So for part A, I'm going to say work is equal to the integral of f dot dl. And then F, of course, is going to be from Newton's law of gravity, Gm, m Earth. So that's the m that would change, of course, if you're doing it for a different planet, over r squared. And r is just the distance from the origin to wherever you're at. Now, I'm going to say that's pointing in the r hat direction, but in this special example, I could have just said, this is the x-axis and I'm doing it in x. And that works fine. Okay, there's no problem whatsoever to do that. Okay, I'm just trying to get you guys used to thinking about spherical coordinates, cylindrical coordinates, that sort of thing. Not because I want you to do all the details, but I just want you to get used to using them, because if you're going into engineering and many branches of science, it helps to have those different coordinate systems. So there's our force. I'll put parentheses around it. I'm going to dot it with DL. And in this case, I'm going to say, let's let the DL dictate which direction I'm going. So I'm going to say positive dr going in the r hat direction. Now, r hat, remember, like all vectors with hats, are supposed to mean unit vectors. So its length is 1 unit, period, not 1 meter or whatever. And in the case of r, it just always points away from the origin. So if I'm here in space, it points that way. If I'm here in space, it points that way. If I'm here in space, it points that way. So it's always just radially away from the center of the Earth, or radially away from the origin of the coordinate system, is what the r hat r is. So now I have to choose the positive coordinate direction for this, because I use this to define my direction. In this case, you see they're both the same, so it didn't matter. But my positive coordinate direction is from r for the Earth, which is that circle with a plus in it, to infinity. And I'll show you how to deal with an infinity in the range of integration in case you haven't covered that in your calculus class yet. So when we go to take the dot product, we can see that the G, the M, and the M are all going to come out in front because they're just constants. So I'll say G, M, M like this. And now I have the integral of dr over r squared. And just like before, when we had I hat dot I hat, we're now going to have r hat dot r hat. And that's just going to be 1, because again, it's 1 times 1 times the cosine of 0. And I'm going to integrate that from r, the radius of the Earth, to infinity. So this is basically the derivative of r to the -2 power, which of course is -1 over r to the 1 power. So this will be negative G M M over r evaluated from r Earth to infinity. So that's going to become negative G M M. And here's how we deal with that infinity. The infinity is the first thing we're dealing with. So I'm going to take the limit as r approaches infinity of 1 over r. And then I'm going to subtract from it 1 over r Earth. So with that, I think you can see the limit of 1 over r as r approaches infinity is 0. So the answer I get is finally work done is equal to G M M Earth over r Earth. And that's the work to escape.
We can't see the work you just did.
I think. Can you see it now?
Yes.
Now, in the next chapter, we're going to learn about conservation of energy, and we're going to introduce something called potential energy. And what you'll learn is that the change in potential energy is always equal to the negative of the work done. So just keep that in mind. Delta U is equal to the negative of the work done, which means basically the potential energy function for gravity, if you're not doing radiuses very small compared to the radius of the Earth, if you're not doing altitudes that are small compared to the radius of the Earth, then you have to use this with a negative sign in it to represent, for any particular radius from the center of the Earth, to represent the potential energy. So that's something that'll come up later. But anyways, that basically means U is equal to negative G M M over R. Okay, so that's the more general expression that we're really shooting for. And now that we know that about energy, we could actually go back and solve all our gravity problems with this and find all sorts of neat stuff, like show that the conservation of energy gives you a velocity for the planet at any particular point, or it could be used to show you that the square of the period is proportional to the cube of the semi-major axis, all that cool stuff. So now let's do part B. Now part B, I'm saying, assume energy or work comes from M's kinetic energy. And that it is only successful leaving if V is equal to C, which is 299,792,458 meters per second, which we really don't need that many sig figs, but that's actually exactly the speed of light. In other words, we've now defined the second and meter in terms of that. Okay, so that's never going to change. There's never, it's basically that to an infinite number of decimal places with all zeros. Okay, so by doing that, by me making the conclusion that the kinetic energy or the work is going to come from the kinetic energy, what I'm saying is I'm just going to set this work equal to the kinetic energy. Well, kinetic energy we learned was either K or KE RT in some cases. And what we learned was that it's 1/2 mv squared. So we're going to take 1/2 the mass of the object trying to leave the Earth times the square of the speed of light is equal to g m Earth over r Earth. Okay, you can see automatically these m's cancel out, which means basically this formula is independent of the mass of the object trying to leave the Earth. So now I can solve for the radius that the Earth must be smaller than to actually be a black hole, and that is given by r Earth would equal 2g m Earth over c squared. And that happens to be the actual Schwarzschild radius that comes from general relativity. It's exactly the right formula. SCHWARZSCHILD radius. And like I said, I just bring that up because it's neat that Newton's laws gives us the actual radius from Schwarzschild solutions. Schwarzschild used a great deal of symmetry when Einstein introduced his general theory of relativity. He used a bunch of symmetry and came up with the what we call a metric, which tells you how to measure how far space is. And in doing so, he basically came up with the idea of a black hole, and he showed that as long as you stay outside of this radius, then the black hole is not necessarily harmful. But once you get within that radius, then you will be sucked in and you will never get out. Not even light could get out. So let's do that calculation. I'll take 2 times 6.67 times 10 to the negative 11th. That's in Newtons meters squared per kilogram squared, times the radius of the Earth, or excuse me, times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. All that divided by the radius of the Earth, which is 6.38 times 10 to the 6 meters.
All right.
Yep.
Everything okay there, Elizabeth? All right, so when you calculate this, you get 8.88. I've actually rounded it already, times 10 to the negative 3rd meters, which you can see is 8.88 millimeters. So that's the actual right answer. And that is the Earth's radius as a black hole. And in fact, that's true for everything. Anything you want to be a black hole, you just have to make sure it obeys the radius is smaller than this, where this is given by 2 times the gravitational constant times the object's mass divided by the square of the speed of light. Now, the other side of this that you can see is when we actually set 1/2 mv squared equal to g m over r. Notice I've got rid of all the references to the Earth at this point. This m still cancels out, and in fact what we find is that is v escape velocity. So the escape velocity is actually equal to the square root of 2g m over r. So that's a nice little extra thing we can do now that we have that. So if you want to calculate how fast something must go to leave the Earth, you can just put that in and find out how many meters per second it is, or how many kilometers per second, or how many kilometers per hour, or miles per hour, or miles per second. Miles per second, I think, is most impressive. And that is essentially the speed that the any spacecraft that leaves our Earth gets really, really close to, because he doesn't really have to go, the spacecrafts to orbit the Earth doesn't really have to escape it all the way to infinity. But we get about that speed anyways. There's actually a slightly different factor if you want to kind of find out what the speed is for it to be form a circular orbit around Earth. But any questions on that? Today's the 8th, right? 10/8. Okay, so that is yet another instance where we've now used a line integral to compute the amount of work done. And I gave you some extra stuff there that's just, sort of for fun. Now let's do another problem. This problem is we're going to use the work energy theorem. And we derived the work energy theorem last time. And what we found was that the net work, in other words, if you take all the forces acting on an object, every one of them, and sum them up, and then do a dot product with them with the DLs and take the integral of it, then that'll be the net work. That turns out to be equal to the change in kinetic energy, which this delta always means final minus initial, so that could be interpreted as 1/2 m v final squared minus 1/2 m v initial squared. Okay. So what I want to think about first is how much work does it take to accelerate a softball to 60 miles per hour? So how much work is required to accelerate a softball to 60 miles per hour? And I think you all remember that 60 miles per hour is about 26.8 meters per second. I'll also tell you that the mass of a softball is 190 grams roughly. Federations actually put limits lower and upper limits. The ball has to be between those two weights to be used valid. It also has a hardness test and all sorts of stuff like that. You can Google all that stuff you want. I think those of you that know anything about softball, women often pitch quite a bit faster than 60 miles per hour, but that's a good speed. That's the speed that you probably, I would think you probably have if you're going to be a really good high school player that might get into a college, even at least a Division II college. Whereas, I think Finch was throwing over 70. So let's go ahead and work it out. Well, work is equal to the change in kinetic energy. So I'm going to say the work net. And really I'm taking into account all the forces. So she might actually have to apply more force if she's throwing to reach 60 miles per hour against air resistance and stuff like that. But at the end of the day, this is the net work just required to accelerate it. So it's 1/2. Notice the m is in both terms, and we're not suspecting the ball to change mass as a result of throwing. So it's going to be the same end in both cases. So I'll say 0.190 kilograms. I'm assuming that's 3 sig figs times v final, which would be 26.8 meters per second squared minus 0 meters per second squared. And that should give me my answer. Worked this out before, but I wanted to make sure my math is working out. So I'm going to do 0.5 times 0.19 times 26.8 squared. And that gives me 68.23. That's exactly the same number I had before, 68.23 joules. Now remember, our model of a joule, or our idea of how big a joule is I told you it's about as much work or about as much energy as it takes to lift a red delicious apple from the floor to the height of a dining room table. Okay, So we're pushing this thing at 60 miles per hour, and evidently we're not, getting really any effect from gravity. We're doing this, or the pitcher's doing this with just her arm, underhanded at that. And in so doing, it's taken about 68 times the amount of energy required to lift the red delicious apple off the floor and onto the table. And that in some sense makes a little bit of sense to me, because the apple maybe is a little bit lighter than than a softball. And of course, we're not just trying to lift it, 30 some inches or whatever. We're actually trying to bring it up to a speed of 60 miles per hour. So that's pretty reasonable amount in my estimation. All right, so that's one problem. Let's do another. So this one, I'm going to talk about that Tesla S Plaid that we mentioned, or that we've worked on before. So the Tesla S Plaid, I would like to know how much work is done in its 0 to 60 record-breaking feet. So how much work is done by Tesla's motor? Notice I said motor, not engine. Electric motors are motors, and gas, quote unquote, motors are engines. Okay, so we're talking about the Model S Plaid. Which goes 0 to 60 miles per hour in 1.98 seconds. And its mass is equal to 2,250 kilograms, which is about 4,766 pounds. Okay. So that's the work we're going to do. And that's part A. And part B, what average power is required? And I'll note, Tesla says their motor has a 1,020 horsepower rating. Okay, if they put it on a dynamometer, that's the device they use to measure horsepower on an engine, that reads out at 1,020 horsepower. So, all right, so part A, let's hit it. So part A is work net is equal to the change in kinetic energy, which is going to be equal to 1 times 2250, or 1/2, excuse me, times 2250 kilograms, times final velocity, of course, is 26.8 meters per second squared minus 0 squared. And this is going to get quite a bit different amount of work. So 0.5 times 2250 times 26.8 squared, and I get 808.02 times 10 to the third joules. Okay, so that's 808.0, giving 1 extra sig fig kilojoules. Okay, so in principle, this is basically lifting 808,000 apples to the height of a table. So that's a pretty big amount of work. Let's see what part B gives us. So part B is where we want to figure out what the power is, and the average power is just the work divided by time. Remember, power is supposed to be dW dt. So B, power is equal to dW over dt. We're talking average power, so we can just take the work done divided by the time taken, and that's going to be 808.02 times 10 to the third joules divided by 1.98 seconds. Okay, obviously that's not horsepower. We're going to convert that, and I'll show you how in a second. So I'm going to do this number, and I'm going to divide it by 1.98. So it should be decreasing it by about a factor of 2, and it does. It gives us 408.09 times 10 to the third watts. Okay. So you remember watts like your light bulbs measured in. So this is 408,000 light bulbs. That's a pretty big amount of power, but you're going to be surprised at how small it really is. It turns out that in fact, 1 horsepower is 746. I don't know why I made that a Z, but I did. 1 horsepower is 746 watts. So we can go ahead and do that conversion by dividing it by 746. And we get 547.04 horsepower. So that's well under what the what Elon Musk is advertising about as Plaid. That doesn't mean he's lying. What's more likely the case is if you actually did a plot of position versus time for this actual run, what you'd probably see is something like this. So most of the power, that 1020 was probably used in the very beginning to get it from say 0 to 30. So maybe it got 30 miles per hour. Maybe it got that in 0.5 seconds. And it took the other basically 1.5 seconds to get up to the 60 mile per hour mark. So that's probably the culprit is, yeah, as I told you before, you can't necessarily assume a constant acceleration. Of course, the velocity versus time graph on such a thing would look like this. This is not uniform acceleration. So we'd see probably something like this. And again, the velocity was 0 and quickly rose, and then it starts to level off. Probably when we get around 40 or 50, it's probably starting to level off. I'm sure it can go faster. I'm not trying to say that's an asymptote at 60 miles per hour, but it would certainly be level compared to the initial takeoff. Any questions on that? All right, and here's a more normal work energy example. I've looked up the coefficient of kinetic friction for roads, and usually roads with rubber tires, usually it's on the order of 0.100. So we're going to say that. And I want to know, assuming we're on a level road, how much work does it take, or not how much work does it take, but how far does it take Tesla to skid to 0? So how far must the Tesla skid from 60 mph to a stop? Okay, so that's a typical problem, and this is actually how the police officers can use your skid marks to determine how fast you were going in a wreck. So they can actually still tell whether you were speeding or not. So, and you're going to be surprised by this. Basically, we know that the normal force counteracts the weight of the Tesla. Okay, that's the free body diagram of the Tesla. So F normal is equal to mg. That means F kinetic is equal to mu kinetic times m times g. And of course, this F is actually acting exactly the opposite direction as the Tesla is going. So when we take the work, which is the integral of F dot dl, where F is friction force, we are integrating to the right and the force is pointing to the left. So we're going to get a negative amount of work. And in fact, the force is a constant. So you know, I just have to multiply it times the distance. So what that tells me is I'm going to get mu sub k, mass of the Tesla, times g, times the distance that we want to know, is equal to 1/2 m v final squared minus v initial squared. Now, it is actually probably, since you're skidding, you're losing a little bit of mass, but it's probably insignificant, so I don't need to worry about that. In this case, the final velocity is 0, so we are going to get our negative. That tells me that D should actually equal, notice the M's cancel out, so this formula is going to be the same, whether it's a Tesla or a Mack truck. So D is in fact going to equal V squared, which V meaning the initial velocity squared, okay, divided by 2 mu K times G. That's the general formula. And you can actually find this formula on tables on the internet I found for Department of Transportation and stuff like that. Transportation engineers use this kind of formula all the time. And you can actually find web pages where the various states departments of transportation are giving these tables, and they're given values in UK. So it's kind of neat that we happened upon the same thing that they're using. And there's corrections for it if you don't want it to actually skid. I mean, modern brakes are made so that they're anti-lock brakes, and that keeps them from skidding, and they're a lot more efficient. But you're going to be surprised at how big this number is. So we write 26.8 meters per second squared divided by 2 times 0.100 times 9.80 meters per second every second. And you see that meter squared up top with the second squared in the bottom is going to just become a single meter, because this is going to cancel everything out. And when I do this, I get 26.8 squared divided by, and I'm going to use parentheses because otherwise it'll divide by the 2 and these will be multiplied by. So I go 2 times 0.1 times 9.8. And that gives me 366.4 meters. So 366.4 meters, that's actually a pretty large distance. And that means, in fact, I think I've already converted it once before. Yeah, that's about 587 feet. Okay. So yeah, skidding is not obviously is not the best way to brake. In fact, I've had incidents where I've skidded to a stop before, but you learn when you're taking driver's ed that you're supposed to pump your brakes, and if you're thinking fast enough, it's pretty easy to do. I basically was going about 70 miles per hour when I noticed a car was about 100 feet in front of me going 0 miles per hour on an overpass. So I fit between the side of the car and the railing of the overpass on the way back from Busch Gardens. And I hit the brakes and I could feel it skid. And then I was losing control of being able to steer around the car. So I let off the brakes, steered a little bit, and then hit the brakes again. They started to skid again. I let off of them and I hit them again. And I managed to go past 2 cars between the railing and the cars without wrecking. So I will tell you that pumping the brake is really a perfect thing, but they ask you not to do that on cars with anti-lock brakes, because the anti-lock brakes does that, but way faster. They go tap, 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 something like on the order of 1,000,000 times per second. So any questions on that problem? All right, well, we only got about 10 minutes left, and I've finished chapter 7. So I'm going to go into chapter 8, which is conservation of energy. And conservation of energy is what chapter 8 is about. So I'll say chapter 8. Whoa, chapter R for some reason. I don't know where that came from. It's weird how my brain does stupid stuff like that. Chapter 8, conservation of energy. So we recognize generally 2 types of mechanical energy. Those types of mechanical energy are potential and kinetic. So we've already introduced kinetic energy. So here's one of them. Kinetic energy, which I told you is K or KE, or even sometimes they use T. And that's generally 1/2 mv squared for point objects. So in other words, objects with no size have a kinetic energy 1/2 mv squared, representing V as the speed that their center of mass is going. However, if an object actually has a physical size, then it'll have a kinetic energy associated with how its center of mass is moving, but also another one associated with how it's rotating. So when we get to rotational motion, you'll see there's another one just like it, and it turns out to be 1/2 I omega squared, where this is called the moment of inertia. watch out, there's a stark difference between that we use in engineering and that we use in physics. So when we get there, you'll see it. Now, the other type of mechanical energy is called potential energy. And I've mentioned that just today. And that is usually given the symbol U, sometimes it's given the symbol PE. And in quantum mechanics, they use the symbol V. Okay, so that's probably the only time I'll use V is when we start studying quantum mechanics, but U or PE is normally what I use. Okay, now what it is remember, work is anything, work can be provided by anything that can drive a nail. And remember, we can consider nails that are literally have a tip that's as sharp as a single atom, right? And then the diameter might be as small as, a single atom even. And then you consider it going into something as soft as melted butter. So anything that can drive a nail, that even at that, or at least at that most easy scale, is work. Well, potential energy is sort of the potential to do work. So for instance, if I step on a nail in my yard, I can drive the nail into the ground. Maybe I can't go very far. For instance, need to aerate my yard and stuff like that. But what if I went out and took a big pickle barrel and stood on top of the pickle barrel and then jumped down and landed on the nail? Then I could drive it hopefully further into the ground as opposed to through my heel, right? So that's the potential energy. It's usually an energy related to position. And sometimes they even call this, 1/2 k x squared for a spring. Sometimes they even call that potential energy. And that's okay, because if you imagine taking a spring that had zero compression and you compress it by a distance x and then latch it down, you basically got a spring-loaded gun, like for toy guns and stuff. But that has the potential to accelerate a ball, a projectile of some sort, and therefore to drive a nail or whatever. So that's one of the potential energies we sometimes use, which we already calculated as the work done in compressing or stretching a spring. The one we're going to use is really, if you imagine lifting an object of mass m using a force F, okay? Well, the force that's fighting you is mg, right? So if you want to calculate the work done in lifting it, I would say the integral from y equals 0 to some height h of the force. Now, if I want to lift it just barely enough to lift it as opposed to giving it velocity, then I'm going to set this from the summation forces in the y direction equals mass times acceleration in the y direction. I will set that acceleration equal to 0 so that I get F minus mg is equal to 0, or F is just mg. So that's the minimum force I can actually lift a mass m with. And by doing so, I'm just doing enough to lift it, but not give it kinetic energy, which is, obviously false, but that's sort of the thing we're considering. So the force I'm going to give it is in the positive direction. It's mg j hat, say. And then I'm moving. I've already chose the positive coordinate direction here. So I'll choose this dl to give me the direction I'm actually moving. Well, I'm moving in the up direction, so it didn't matter either way. So I'm going to say positive dy j hat. And when I get that, I think you can obviously see it's going to be the integral from 0 to h of mg is out in front, and I just get dy j hat dot j hat, which again is 1. So I just get mgh. And that's the typical potential energy that we use, as long as we're not dealing with heights above the Earth that are comparable to the Earth's radius. Okay. And you might say, well, h above what? Well, the good news is the only thing that matters with these energies is not their absolute value, but specifically their value relative to somewhere else. So you're allowed to call the 0 of height any point you want, as long as you stick with that during the problem. No problems will arise. So now that I've introduced these energies, I'll tell you that your book tends to call conservation of energy this expression right here. They would say delta U plus delta K is equal to 0, or they might say delta PE plus delta KE is equal to 0. And you can see that's basically the same thing as saying, you could say U initial plus K initial equals U final plus K final. That actually is the same thing, because all you have to do is subtract UI from this side, and whatever you do to one side, you got to do the other. You get UF minus UI. That's the change in potential. And then you subtract KI from both sides, and you get KF minus KI. That's the change in kinetic energy. So this is a perfectly fine version, but it's a little bit limiting, and that's sort of what they want you to do. They want you sort of to see conservation of energy sort of like a Ziploc bag. And the Ziploc bag right now only has 2 baffles. So it has this little semi-permeable membrane between the 2 baffles. And one of the baffles is potential energy, and the other baffle is kinetic energy. And the total amount of air in the Ziploc bag can't really change, but you can, for instance, squeeze the U until the K becomes fatter. Or you can squeeze the K until the U becomes fatter. When you're squeezing the K, that means like you've thrown something upward, and it slows down as the potential energy increases. That's really what conservation of energy is. But this version is, to me, kind of limiting, because I like to take into account the idea that you can actually allow for dissipative forces. So what I say, and you're allowed to use this now, okay? You can use this. It's not in your book. It's not a numbered equation or anything. But what I do is I'll say potential energy initial plus kinetic energy initial plus work put into the system. Okay. So I'm actually now like putting a little pipe here that allows some air to come in it, right? As long as I keep track of that, then we're still going to get a valid equation. Well, that's going to be equal to U final plus kinetic energy final plus work put out, plus I'm going to allow for E loss. So for instance, friction forces, like we showed stopping the car earlier, that can be put in there. Or we can let the object run into a spring and actually compress the spring, and that can be put in there. And in fact, it's some ambiguity into what this is, and what this is, right? In fact, you might call this the friction force, and this the 1/2 kx squared, or the friction work, and this 1/2 kx squared, whereas someone else might say, well, I see the energy being absorbed by the spring, so they put the 1/2 kx squared here, and they'd say, well, I saw the friction heating up the ground, so that's work done on the ground, and they put it right here, and that's fine. The only thing that you need to make sure you do is you account for each source of energy and each loss of energy exactly once. As long as you do each one exactly once, it doesn't matter where you put it, okay? So the typical problem I give my students, and I'll do this really quickly because we only have like 2 minutes. The typical problem I give my students, just to show them how this could possibly work and see all the different terms, is I imagine a kid at the top of a flat hill, and then at the bottom of the hill, there's a safety mat that's got a huge spring that stops the kid from, running into traffic. The kid is going to be on a sled, in fact. And their dad's going to push them. Okay. So we could say the work in is the father pushing with a force of 100.0 newtons over a distance d equal to, let's say 2.00 meters. Okay. We could say this height right here, h, is 100.0 meters. That'll be our h. Okay. And we could account for instance, the friction by saying this distance right here, this distance is, let's say 500.0 meters. I'll call that d prime since I already used d there. We'll say the coefficient of kinetic friction, UK, is 0.100. And we'll say that the normal force on average is about 0.85 mg. Because remember, up here, the normal force will be mg. But then as it gets on the incline, it's going to be mg cosine theta, mg cosine theta, mg cosine theta, mg cosine theta, mg cosine theta. Then it'll be mg again. So this is a way I've found to approximate that. Okay. And I'll say the girl in the sled has a total mass of 50.0 kilograms. Okay. So the question could be, V there is equal to what? Just before they hit the thing, how fast are they going? And then that would be part A. And then part B, how far is the spring compressed? So just, I'm going to write this out because we only got, well, actually a little bit over a minute over. I'm going to say 50 times 9.8 times 100.0 plus 0, because her kinetic energy when the father starts pushing her is 0, plus the work in, which would be 100.0 times 2.00. That's the work in, is equal to U final, which is 0, and is equal to 1/2 times 50 times V final, which is what we're looking for, and that's squared, plus when we're looking for the final velocity, we're not talking about compressing the spring yet, so there's no work out, but there is a E loss, and that would be 0.10, that's the mu, times 50 times 9.8, so that's the mg, times 0.85, and then times 500.0. So that's all the terms you can now solve for V final, and that would get you to V final. When you're done with that, that would just be part A. And when you're done with that with part B, all you really have to do is say 1/2 of 50.0 times whatever that V final squared, whatever that was, is now going to be equal to 1/2 K X squared. And let's say K is equal to 10,000 newtons per meter. So that's all you have to do part B, is just solve for X. That's it. I'll give you the answers to this later. You might want to try it over the weekend, but yeah, your chapter 8 homework's not due until next Sunday. And that's for, I think that's for your problems. And then Wednesday next week is when your, or excuse me, the following week is when your actual problems are due. So the conceptual stuff's due not this Sunday, but next for chapter 8. Chapter 7 is definitely due this week and Wednesday. I would definitely start on them anyways, but actually taking the practice midterm is really good practice for preparing for this. And actually, I've given you everything you really need to know just by this one example. So we're essentially done with chapter 8 in some sense, but I'm going to work a lot more examples. Everybody's free to go. Give me any, ask me any questions you might need to. I'll wait for the last person to leave. Yes, there are conceptual questions on the midterm. And there's conceptual questions in the midterm practice as well.
This video will be posted for us to review before the midterm, right?
Yeah, it should be finished. It should be posted sometime today.
Okay, awesome.
Subscribe to my YouTube channel, and you can, unsubscribe anytime you want to later. It'll make an announcement every time I post something. That's what I'd recommend you do, because I'm posting it there because I find that it's just a lot easier and better quality. Anybody else have any questions?
I just have one question about a grade,
Okay,
which it just may be late to be put in. But my chapter 5 homework, it says I have like a 22.06% on your grade, but in my actual chapter 5 homework, it says I got an 80.
Okay, so all I have to do is it's actually set to automatically update, but that usually takes like 24 hours. So if you've done work recently, that would make perfect sense. Or if I didn't set that automatically to automatically update, then that would make perfect sense. But I'll go and update it now and set it on automatic, and hopefully that should correct it. Just make sure you keep an eye on it by the end of the semester. If it's still wrong at the end of the semester, that would harm your grade, and I don't want to do that.
Yeah, that's why I'm checking on it now, just to make sure I get like the midterm grade that I want.
Yeah, if it makes you feel any better, at the end of the semester, I downloaded the grades from Mastering 2, And I end up using those grades instead of the ones that my grade book says, just to make sure in case something weird like that happens.
Awesome. Thank you so much, Professor.
You're welcome.
When are your office hours as well?
I actually just do them by appointment. So if you ever need to meet with me, you can just send me an email and say I'd like to meet with you, or you can text me because I gave you all my phone number. Don't forget. So you're welcome to text me, and I can set up a private Zoom meeting. And if you tell me you want it private, I'll set it up private. If not, I'll make it available to everybody. So feel free to ask me anytime, Mary.
Thank you very much. You have a good rest of your weekend.
You too.
Professor, how many questions are on the midterm?
I think I'm looking at, if I remember correctly, it was like 16.
Oh, okay. Thank you.
No problem.
Have a nice day.
And they're different numbers of points each one.
Okay.
Gavin, did you have anything?
I did actually, yeah. I saw there was I was basically wondering about these scores on Canvas. Let me take a look at this. I think it was
Mastering scores like Mary was just talking about.
No, I think it was the lab actually.
Okay.
Let's
That
see.
means since we're talking about your grades, I'm gonna go ahead and stop the video.